Hello everybody again, thanks for tuning into this video on vectors, the first video of this new topic today. So in this chapter we're going to be exploring vectors, in particular the idea of a column vector, where we have two numbers, one at the top and one at the bottom. Now you may have seen already at GCSE, in fact I'd be quite surprised if you haven't seen this already, that we can use vectors to describe translations of shapes, where the top number means how far we move to the right. The bottom number of a column vector means how far we move up or down if that number is negative. Now there are also other uses to vectors, for example in the mechanics side of the course, and as well in order to prove certain geometric properties of shapes. But this is all still to come in this chapter, so I'll let the worked examples do the talking. For now, let's have a look at the warm-up section of this exercise. So here's the 4 questions I want you to have a go at first and foremost, before we move into the main bit of the lesson. Try these yourselves, without my help first and foremost. So press pause now if you're watching this video remotely. Try the questions, then press play only when you've attempted your best effort at all 4 of these warm-up questions. Okay, so let's have a look together at warm-up question 1. So for question 1, we have 2 triangles, A and B, and we need to describe fully the single transformation from shape A to shape B. Now this one is just a bit of GCSE revision. So what I'd be thinking of first of all is, has the shape grown or shrunk? It's not, so it's not going to be an enlargement. Has it rotated? No, it's not, so it's not a rotation. It's still the same way round, it's not been flipped, so it's not a reflection, and so what this is it's a translation. Shape A to shape B, it's just moved from one position to another. So we can say definitely it's a translation. And the same for part B as well, from B to A will also be a translation. A translation is where the shape doesn't change size or orientation, it just looks to have moved from one location to another one. So we describe translations by what we call column vectors. So for part A, from shape A to shape B, we can work this out by just picking one point on shape A and the corresponding point on shape B, and then thinking about how we move from the point on the original shape to the point on the new shape. And so from shape A to shape B, what's happening here is we're going to move 3 squares to the right and 1 square up. So the column vector will be 3 at the top and 1 at the bottom, which denotes we're going 3 to the right and then 1 up. Now for part B, if we're going from shape B to shape A, it's the same idea but just in complete reverse. So we're going from shape B to shape A, so again it's going to be a column vector translation. So this is a translation by column vector, and this time we can pick any point on shape B and then think about where this moves in terms of getting back to shape A. So for this one, it's going from this point here to this point there. So this time we're going 3 to the left and 1 down. Now if we're moving to the left, that's given by a minus number, so it's minus 3, which moves 3 to the left, and because it's going 1 down, instead of being positive 1, we say that's minus 1. And so if you notice here, it's the same magnitude of these numbers, but opposite signs, because we're moving in opposite directions as we go from B to A, rather than from A to B. So that's question 1 done. Question 2, we have a line, and P is dividing this line AB in the ratio of 5 to 3, where AP to BP is 5 to 3. So P is somewhere on this line. So first of all, for part A, we need to find the ratio, expressed as a fraction, of the length AP to AB. So if we think from A to P, from A to P, we're told is 5 parts long. And so from A all the way to P is 5 units. And likewise, from P to B is 3 units. So we can add this on here as well. And so if we think about this as a total line from A to B, if we go all the way from A to B, like so, that's going to be 5 units plus 3 units, which is going to be 8 units in total. So now we have all the information in order to solve this question. So for part A, AP to AB, from A to P is 5 units, and from A to B is 8 units, so that's 5/8. For part B, PB over AB, from P to B is 3 units, and like I mentioned before, from A to B is going to be 8 units. And finally, for part C, where we have AP over PB, from A to P, again we can see that's 5 units, whereas from P to B is 3 units. And so A, B, C is 5/8, 3/8, and then 5/3 respectively. Moving on to question 3. We're told here the length of time t, where t is given to the nearest minute, spent on the internet each evening by a group of students is shown in this table here below. So we need to estimate the lower quartile. So this is a case of applying what we did in the stats part of the course, which is called interpolation. So this is linear interpolation. So if you want to revise this skill, and you forgot what it was called or how it works, it's called linear interpolation. Inter, as in we're going to be reading amongst, within this data, to find a suitable estimate. Linear because this is going to be a linear relationship we're going to use for our estimation. So lower quartile. So first of all, what I'm going to suggest we do is we think about t in terms of the bounds of t from the beginning to the end. Now t is time given to the nearest minute. So for this first interval, the lowest value of t that would still be recorded and rounded up to 15 to the nearest minute would be 14.5. Anything lower than 14.5 wouldn't have made it into this interval. At the higher end of this interval, the boundary in between 24 and 25 minutes, the absolute cutoff would be 24.5. So I'm just going to ring t in blue so that these blue numbers relate to t. Between 37 and 38, that's going to be 37.5. The boundary in between 46 and 47 would be 46.5. And the absolute upper bound here at 60 would be 60.5. Yes, you might be thinking if it was 60.5 exactly, it would round up to 61, but because t is continuous, we can get infinitesimally close to 60.5 and it still round to 60. So if it really makes you more comfortable, you can think of this as being 60.49 recurring, which actually is exactly the same as 60.5, but ask me that in lesson if you don't believe me and I'll try and convince you. This upper boundary is 60.5. For f, so we're just going to do a running total of frequency. We're going to do a cumulative frequency here. Starting before anything happens, the frequency is 0. After 11, we've got 11. 11 plus 6 is 17. 17 plus 5 is 22. 22 plus 14 is 36. So now we've got all the ingredients, we can estimate the lower quartile. So the lower quartile is going to be, because it's continuous data, we just take the total here, which is 36, and we're going to divide that by 4. Lower quartile, first quarter, so take the total frequency, which is 36, and divide that by 4. It's going to be not 9, but that number value. So the 36 over 4th value, which is going to be the 9th value, because 36 over 4 is 9. So we're after the 9th value. So where might that lie? So we want the ninth value, okay? So it's going to be in between 0 and 11. So the ninth value is going to be somewhere here. We don't know exactly where, we can only estimate this. So the ninth value is going to be somewhere here. So next what we do is we think that the ninth value is going to be somewhere in the interval from 15 to 24. We'd imagine the ninth value is going to be 9 out of 11. Okay, so it's the ninth one, the ninth value, out of a total of 11 in this interval. In the interval from 15 to 24. And so we're going to estimate the lower quartile, which is Q1, remember, is going to be approximately, this shows it's going to be an estimate, it's where the first interval begins, so it starts at 14.5. Then how far into this interval do we need to go? Well, the full length of the interval across would be 11 values. We only want the ninth value, so we want 9/11ths of the way into this interval. So it's 14.5 plus 9/11ths of the way along this interval. So now we need to think about the length of this interval, the width of it rather, the class width. From 14.5 to 24.5, that's going to give us a class width of 10. So the class width of this interval is 10. So we start at the beginning of the interval, that the lower quartile is in, and we want to go 9/11ths of the width into that. And it's 9 because it's the ninth value, and there's 11 in this interval, 11 values. So now all we need to do is use the calculator and round to a suitable degree of accuracy. And so if a question doesn't say, if in doubt, use the golden rule, give it to 3 sig figs. So we're going to do 14.5 plus 9/11ths of 10, which gives us 3 sig figs, 22.7. And so our estimate for the lower quartile is 22.7 minutes. Finally, question 4. This is a bit of revision again from stats. So we've had a variable x which has been coded into y, and we're told that the standard deviation for y is 4.57, where y is coded from x according to this. So we need to find the standard deviation of x. So in plain English, all that's happened is we've had a variable x, we've subtracted 5 from all values for this variable x, and then divided all of these values by 10. And so which of these numbers, 5, 10 or both, is going to affect the standard deviation of x? We need to remember, if we plus or minus a constant from a variable, it doesn't affect the standard deviation of that variable. It just shifts the whole lot up or down by the same amount, but amongst themselves, because all values of a variable are shifted by the same amount, they're still, relative to one another, the same spread apart. And so this minus 5 is irrelevant. The only thing affecting x is that all values have been divided by 10 to achieve y. And so what we can say here is that the standard deviation of y, sigma y, is 4.57. That's after x has been divided by 10. So we can go back and work out the standard deviation of x by multiplying the standard deviation of y by 10. And we don't need to worry about this minus 5 at all. That would only affect the mean or the central tendency. It would not affect the spread in any way. So the standard deviation of x is going to be 10 lots of the standard deviation of y. So we undo this dividing by 10 by multiplying by 10, and we're multiplying by 4.57 because it does say that the standard deviation for y is 4.57. So if we do that, we don't need a calculator. Use one if you really must. 10 multiplied by 4.57 is 45.7. And that concludes the warm-up, so we can now get on to the main part of the session. Okay, so let's now have a look at some definitions of vectors. So, first of all, a vector is a mathematical object that has both a magnitude and a direction. So it has a size and it's going somewhere. Vectors represented by directed line segments. In other words, they look like arrows on diagrams. So here are two vectors. This one here is going from A to B, so this one would be A, B. This one here is going from B to A. This vector would be BA with a line going over it, or because it's the same magnitude but opposite direction, BA we could say is minus BA. So this one we could write as AB. This one here is going from B to A, and because it's equal but opposite to AB, we can say this is minus AB. So just a little introduction to how these can be expressed. These are another two pair of vectors. So we've got from P to Q and then from R to S. So these two are the same size, the same magnitude, and going in the same direction. So because of that, if PQ is the same as RS, then we can say that the line segments PQ and RS are equal in length and they're parallel. And so they're exactly equivalent. So we can say that PQ is the same as vector RS. Addition and subtraction of vectors. So vectors can be added and subtracted. So first of all, addition of vectors. You can add two vectors together using the triangle law for vector addition. So if we have a triangle here, ABC, and we call the vector from A to B, A, and the vector going from B to C, B, then AB plus BC is equal to the vector from A to C. In other words, A plus B equals C, like so. So what we can say here is that AC is called the resultant vector. The resultant vector is the sum of two or more vectors. So the resultant, in plain English, is the overall effect of what we get when we add a multitude of vectors together. It has a net effect, which we call the resultant. For example, in physics, if we have more than one force acting on a body, the overall effect of that force can be given by a vector called the resultant force, which is the size and direction of the overall effect of all those forces acting on the one body. It can be considered as one force, which is called the resultant. That's addition. So what about subtraction? Same idea, but just opposite, really. The same as subtraction is similar to addition in numeracy, but just the opposite idea. So subtracting a vector is equivalent to adding a negative one. That's the most powerful way of thinking about it. So if we've got here vector A going upwards in this direction, and vector B going upwards but slightly to the left, then we can think about A minus B as A added to minus B. So if B is like this, then minus B will have the same direction, the same size, it's going parallel, but just going the opposite way. So in other words, if this is B, then this is going to be minus B. Now if you're writing vectors, you can't differentiate standard text from bold text unless you've got two different type pens, like maybe a felt tip. What you can do is just do a little line underneath to denote it's a vector. So if this one's B, minus B is like this. So A added to minus B is the same as this resultant here, A minus B. And you can think about vectors in terms of travelling. It's almost like a road map. Okay? So if you travel from P to Q, and then back from Q to P, you are back where you started. So the displacement, the overall effect is 0. So in other words, if you've got a vector that goes from P to Q, and then you add on to that the vector from Q to P, one undoes the other. So the net effect is 0. And 0, bold 0, is called the 0 vector. In other words, you've gone a distance of 0, and the direction is meaningless because you've gone nowhere. So 0 itself you can think of as a vector, just no movement in no direction. You can also multiply vectors by a scalar, where scalar just means just a number. So all a scalar means here is just a number. So a scalar is not a vector, it's just a number with just size only, no direction. So 4, 5, 6, pi, whatever. So imagine you got here vector A. Imagine multiplying that so it's bigger, has a bigger magnitude. If I multiplied A by 3, I'd end up with 3A. So multiplying by a scalar does not change the direction, it just changes the magnitude. So 3A, the size is kept the same because 3 is positive, but the magnitude of A is multiplied by 3. What if we multiplied by a fraction? What if we went from A to half of A? Half of A would be half the size, so it only becomes half as long. So that's if we're multiplying by a positive scalar. Now if I introduce another vector B, think about what would happen if we multiplied by something negative. For example, multiplying it by 2, if it were positive 2, would double the magnitude. So the line length would be represented by a line double the length of this one. But if it were minus 2 we multiplied B by, B, this line here would still be double the length of this, but would go in the opposite direction. So the minus sign switches the sign of the vector. The direction goes in the opposite way to what it went before. If we multiplied B by half, we'd have half B, somehow we had half A here. But if we multiplied by minus a half, it'd be the same length, but again, the direction of the vector would be switched. So rather than going to the right, we multiplied by a minus scalar, the vector would be going to the left. So to summarise this, if the scalar is positive, and it's not 1, the new vector has a different magnitude in the same direction. If, however, the scalar is negative, but not equal to minus 1, then the new vector has a different magnitude in the opposite direction. Generally speaking as well, any vector that's parallel to the vector A can be written as lambda A. This symbol here is lambda, and it means lambda is a non-zero scalar. So if two vectors are parallel to one another, we can write one as a multiple of the other. That's all it's saying. Now let's consider some worked examples. So vector addition, subtraction and multiplication. So let's have a look at worked example 1. So here for question 1, we've got vectors A, B and C illustrated below. And we're going to use these vectors to draw diagrams for each addition and subtraction question for parts A, B and C. So for part A, on the grid you've got, draw a diagram to represent the vector addition A plus B. And so what we're going to do here is the first vector A, we're going to draw out. So this one here, A, goes 2 along and 3 up, as you can see. So 2 along and 3 up, that's vector A. So I'm just going to label this on, that's vector A. Now when we're adding vectors, the vector we're adding, the tail of it goes at the end of where the previous vector started. So we join the tails to the arrowheads, if the arrow means the end of a vector. So because we're adding B, the next thing we're going to do is, starting from the head of the previous vector, we're going to put the tail end of B here. So starting at B over here, B, as you can see above, goes 4 along, 1, 2, 3, 4, and 1 down. And so this one here is vector B. And so the resultant vector, which is A plus B, we're starting at A and we're ending up over here. So we're starting at the tail of A, I mean to say, and ending at the arrowhead of B. And so the vector from A to B is going to be, I'll do this in a different colour, represented by this vector here. And so this vector in red is A plus B. And just to make that perfectly clear what I'm talking about, we're not talking about just A on its own or B on its own, we're talking about A plus B combined, which is this line here, done in red. It's probably not quite thick enough, I'll just do it in a thick yellow to make it perfectly clear. It's this one. So question B is the same idea. So again on the grid, we're going to do A plus B plus C. So start with A goes 2 along and 3 up. So 2 along and 3 up, like so. Then join that onto B. So B goes 4 along and 1 down. So B is 1, 2, 3, 4 and 1 down. Then C is just 2 units straight down, like so. And so I can label this on. So this one here is A plus B plus C. Then the resultant A plus B plus C is just going to be going from here through to there. So A plus B plus C is this one along the bottom. Again, just to make that really clear, highlight it in yellow, and job's a good one. Finally, part C, we're going to draw on A minus B, and so it's minus B, so it's going to be the same magnitude as B, but going in the opposite direction. So first of all, let's start with A, but because we're going to minus B, I'm going to give myself more space on the left-hand side. So A, now you can start with vectors wherever you want. The only important thing is if you have the right size, going in the right direction. So vectors you can drag and drop to wherever you want to, as long as you don't rotate them or blow them up in terms of getting them bigger or smaller. So I'm going to do vector A here to make sure we've got enough space. So that's 2 along and 3 up. And then minus B, well, B is 4 along and 1 high, if you like. So this time, rather than going 4 to the right, because it's minus B, I'm going to go 4 to the left, like so. And instead of going 1 down, I'm going to go 1 up. And so, just labelling this on. This one's A. This is minus B. And so A added to minus B, the overall effect of that is going to be that we start here and we go up to this point like so. And so A minus B is this vector here. Now before we go on, just a little note in terms of doing this more mathematically, rather than having to sketch out diagrams in your test, which you're not going to be doing, I do not believe. If we think about A is going 2 along and 3 up. So think about A as being 2 along and 3 up. B is 4 along and 1 down. Now look at A minus B. A minus B, we're going 2 to the left, so it'd be minus 2, and then we're going 1, 2, 3, we're going 4 up. Okay? And so, pardon me, B is 4 to the right, 1 down, so B is minus 1 down here. So A minus B, excuse me, would be this vector 2, 3, minus this vector 4, minus 1. But we can see here for A minus B, just using the diagram, just by drawing it, we've gone 2 to the left, so minus 2, and overall we've gone 1, 2, 3, 4 up. And so in terms of doing this without having to draw it, just look at the horizontal components. 2 minus 4 is minus 2, 3 minus minus 1 is positive 4. So we can do addition of vectors just by considering the top numbers, either added or subtracted, and the bottom numbers done separately, either added or subtracted as appropriate. So actually it's very, very simple once you get your head around it. Question 2. Show that the vectors 6a plus 8b and 9a plus 12b are parallel. So just reminding you of what we did earlier in the notes. We need to remember this, that any vector parallel to vector a can be written as lambda a this is, where lambda is a non-zero scalar. And so all we're saying here is that if two vectors are parallel, we can write one vector as a multiple of the other. So starting off with 6a plus 8b. 6a plus 8b. I'm just underlining a and b to denote that these are vector components. We can factorise this, just as you'd factorise normal algebra. 6 and 8 are both even, so we can write this as 2 lots of 3a plus 4b. Similarly, with 9a plus 12b, we can factorise out a 3 from these, so we can write this as 3 lots of 3a plus 4b. And so 6a plus 8b I can write as this, and 9a plus 12b I can write like that. So now we can think about how 9a plus 12b relates to 6a plus 8b easier, because they both have a factor of 3a plus 4b. So next we can say that 9a plus 12b, because that's 3 lots of 3a plus 4b, well, 3 lots is the same as this 2 lots multiplied by 1.5. So it's actually 1.5 times as big as 2 lots of 3a plus 4b. Sorry, of 3a plus 4b. So what I'm trying to say here is that 9a plus 12b is a multiple of 6a plus 8b, because 6a plus 8b I can rewrite as 2 lots of 3a plus 4b. And so this vector here is just some multiple of the other one. So we can just conclude by writing this out. So therefore, 9a plus 12b, it's a multiple of 6a plus 8b. And this therefore implies that 9a plus 12b and 6a plus 8b are indeed parallel to one another. So for questions like this, all we need to do is just show algebraically that one set is some multiple of the other. So here we can show that 9a plus 12b is 1.5 times this thing here. If we take this and multiply it by 1.5, we get that. That's probably an easier way of saying it. Question 3. Question 3, 4 and 5 in fact, and what I like to sort of think of as roadwork type problems. It's route planning, you've got your sat-nav, how do you pick your route? And it's a case of you can go down any route you want as long as you know what that route is or the road is in relation to a vector. So this first one, it makes sense when we do them, trust me. For part A, we need to go from P to S, and there's some information here. So for example, from Q to P is A, from Q to R is B, from Q to S is given by vector C, and from R to T, that's going to be denoted by vector D. So we need to go from P to S. And so let's just think about how we can do this using the vectors we know. So P to S. So we want to go from here to there. So how can that be done? So from P to S, well, one way we could do it is we can go from P to Q, and then we can go, when we get to Q, to S. So we can go from P to Q, and then from Q to S. So PS we can do by doing from P to Q, then when we get to Q, we can go from Q to S. So let's just colour in what I mean here. So from P to Q, I mean along here, and then from Q to S, down this way. Now from P to Q, that's going against the flow of traffic in terms of direction of A. A is from Q to P, and so PQ, because it's the same road but the opposite direction, that's minus QP. Now Q to S, that is going along the same line of traffic as C. So from Q to S, that is the same as vector C. So that's no worries at all. So we can leave that as it is. But we want this in terms of vectors, these letters A, B and C. And so from Q to P, we're told that's vector A. So minus QP is the same as minus A. And from Q to S, that's vector C. So it's minus A plus C. Now, with algebra, we normally write the positive things first, and then write the negative things as what we're subtracting. So minus A plus C isn't wrong, but it's probably more normal to write this as C minus A. So let's have a look at another one. So let's try part B. From part B, we're wanting to go from R to P. Okay, so where the diagram is R, where is P? So from R to P, what we're doing is starting from R, going all the way up to P. So it's this big diagonal here. So using the vectors we can see how we're going to do that. So from R to P, using the diagram, what we could go is go up to Q. So if we go from R to Q, first of all, and then once we get to Q, we can go from Q to P. So then we can go from Q to P. So just colour coding this, and from Q to P, like so. Now consider RQ. From Q to R is B. Okay, so from Q to R, like you can see here, that's B. So from R to Q, because it's the same road, it's the same line, but going the opposite way to the direction of B, this is going to be minus B. QR is B, therefore RQ is minus B. And plus, so put a plus here. From Q to P, that's vector A. It's along the same road in the same direction, so we just call that A. And then we're done. That's it, just minus B plus A. But like I said here, normally write the positive vector or vectors first, so call that A minus B. So hopefully you can see it's just like a road network. We just pick the roads we know to get to where we need to go. So for C, we're wanting to go from P to T. So same idea exactly, how do we go from P to T? So let's just think about where P to T is. So start at P, which is, where is it? Here. We want to go to T. We don't know of a vector going directly from P to T. This isn't labelled with any arrow or vector. So how are we going to go from P to T? Well, I don't know really. I suppose we could go from P to Q first. So we could start at P and go to Q. Then once we're at Q, we could go down to R. So then plus QR. And then when we get to R, we could go along D to get to T. So we could go from R to T. So we're going around the houses. It's not a very direct route, but it gets us to where we want to go. So we could go from P to Q. We'll get to Q, go down to R. So we could go QR. When we get to R, go along from R to T, which is RT. So now we just need to put this in terms of the vectors rather than the capital letters. So from P to Q, it's the same road as A, but it's in the opposite direction. So rather than calling it A, because it's the opposite direction to A, that's minus A. From Q to R, that's along B in the same direction as B, so that's positive B. And from R to T, it's along this one D in the same direction as D, so we call this positive D. And then we're done. But again, in the same way, we normally write the positive vectors first. So I'd say we might want to write this as B plus D minus A. Finally, we come to part D of question 3. So for part D, we want to go along from T to S. So TS, we start at T, we're going to go up to S, like so. So how can we do that? Well, starting at T, how do we get to S? What we could do is go along from T to R. So we could do TR. Then once we get to R, we could go from R to Q. So we could go from R to Q up here like so. Then once we get to Q, we go along from Q down to S. From Q to S will take us to S. So starting at T, we go along from T to R to Q to S. So finally, we do that route. So in terms of vectors, from T to R, it's along this one D, but in the opposite direction to D. We're not going from R to T, we're going from T to R. So that's going to be minus D. From R to Q, we're going against the grain of B. We're not going from Q to R in this direction, we're going against B, so that's going to be minus B. But from Q to S, we are going in the same direction as C is pointing, so that's positive C. And that's it. But again, like I've shown you for A, B and C, this is probably best written as a positive vector first, C, then minus the vectors which are negatives. So then minus B, minus D. Question 4, a similar idea to question 3 really. We've got this parallelogram A, B, C, D. So A to B is A, and A to D is B. So from A to B is vector A, like so. And then from A to D is B. So we need to find from A to C. Now, using vectors, we can also use geometry facts of shape. So a parallelogram, get my teeth in, a parallelogram is what I mean to say. We need to remember, a parallelogram means that its opposite sides are the same length and parallel. So in terms of applying that to vectors, the opposite sides of a parallelogram can be represented by the same vectors. Think about the side lengths as the magnitude. Same magnitude vector, same length of side, and the parallel. So if this is AD, then BC we can represent by the same vector. So whether that helps us or not, I'm just going to say that from A to D is the same as from B to C. So in other words, if A to D is vector B, then B to C will also be vector B, because it's the same size of side and exactly the same direction. So BC equals AD equals B. And in the same way, this top line here from D to C, that's the same size and direction as from A to B. So in other words, from A to B, from D to C, which is the same as from A to B, must be also vector A. So finding the vector AC. So from A to C, think about how we could do this on a map. So to get from A to C, we could go from A to B. Then once we get to B, we could go from B to C. So it could be AB plus BC. But like I said earlier, from A to B, obviously we know that's A. But then from B to C, here, BC is the same as AD, which is B. So it's just simply A plus B. So even though a vector might not be explicitly written on, as it isn't here, if we know well enough the geometry of the shapes, if we're told in the question a shape is a particular kind of shape, we can use that to our advantage and fill in the extra information using geometrical facts of certain shapes. So we can deduce some stuff from the question with growing confidence once we get used to the idea that vectors can just be a representation of geometrical shapes. Finally, question 5. In triangle ABC, from A to B is A, and from A to C can be represented by vector B. P is a midpoint of AB, and Q divides AC in the ratio 3 to 2. So we need to write, in terms of A and B, these following vectors as below. So first of all, we need to think about from B to C. So from B to C, starting at B and going through to C. Now what I'm going to do here is actually write on what we've got. So from A to B is A, and from A to C is B. So even though we want to go from B to C, I'm just going to write on this information here, that from A to B is A, and from A to C is B. So just adding this on, we have this. So next up, what we need to think about here, I'll just pop in as well, because it's sort of gone over. P is about here, and Q is about there. So, like I was saying, from B to C is along here. So how do we get from B to C using these vectors we know? Well, starting at B, we can go to A, then once we get to A, we can go to C. So BC is the same as BA plus AC. But from B to A, that's opposite in direction from A to B. So it's the same as minus AB, then from A to C. Now AB is A, so minus AB is minus vector A. Then from A to C is vector B. So from B to C is minus A plus B, which can be written as B minus A. Part B, we need to go from A to P. So let's just clear off what we've written here so far, from A to P. So starting at A, we need to get here to P. So I'm just going to lock in these little notations for where A, so for where P and Q are, so that doesn't move. So from A to P, we're wanting just this tiny section of AB. We're wanting this bit here. So from A to P, it's along AB. Okay, it's along the road that goes from A to B, but it's not the full way from A to B. So how far along the road AB is P? Well, it says P is a midpoint of AB. Midpoint means you only need to go half the way along. So rather than going all the way from A to B, we just need to go half the way from A to B. Now the vector from A to B is given by bold A. So AB is A, but we want half of that, so half of AB is half of vector A. It's as simple as that. We're just multiplying vector A by this fractional scalar to show that we're not going the full distance from A to B. Let's have a look now at part C, from A to Q. From A to Q, we're going along the road from A to C. So again, it's very similar to part B. So from A to Q, we're going along the road which takes us from A to C, but we're not going the full way. So rather than going all the way from A to C, it's just going to be a fraction of AC. Now this is where this information comes in very handy. And so P is a midpoint, but Q divides from A to C in the ratio 3:2. And so AQ is 3 parts long, and from Q to C, that's the remaining 2 parts long. And so from A to Q, AQ as a fraction of the total from A to C, AQ is only 3 parts, according to this ratio, but from A to C is this 3 parts plus the other 2 parts, which is 5 parts. So in plain English, from A to Q is just 3/5 of the total length as we go from A to C. And so AQ, we only need 3/5 of the length from A to C. Now in vector form, because from A to C is given by vector B, we can write this as 3/5 of B. Finally, part D, let's think about how we can do this. We need to go from P to Q. So, from P to Q, we're going to start at P and go along to Q. So, how could this be done? From P to Q. So, what we're wanting to do here, start at P, go along to Q like so. So, how can we do this? So, one thing we could do is we could go from P to A and then go from A to Q. So, from P to Q, we should have done this green line. We can start at P and go up to A. I'll do this in a yellow colour, quite like yellow. But once you get to A, we can go from A, go down to Q. So, PA. Well, PA is going the opposite way from what A to P is going. So, PA is opposite what we have from A to P. Now, from part B, from A to P, we had as a half A. So if AP is half A, then PA, which is negative AP, is going to be negative 1/2 A. So we can use the previous parts of this question to help us with this part. And then from A to Q, we did that in part C. So from A to Q is 3/5 B. So plus AQ means plus 3/5 B. Which, writing it as a positive vector first, we can say that's 3/5 B minus 1/2 A. And we're done. So just think about it as a roadmap. Sometimes as roadblocks, you need to go out of your way to get to where you need to go, and think about it in terms of if you're going with the flow of traffic, if you're going in the same direction as a vector, it's positive. If you're going against the flow of traffic, that's negative. So it just takes a bit of practice and you'll soon become masters at this. So now it's over to you lot. So if you could turn to page 234, exercise 11A, try questions 3, 4, 5, and then from 8 to 11, and do your best at mastering these by checking your answers after every question using the back of the book, and coming to achieve or asking me in lesson if you're stuck on any one of these. You need to master these because they come up not just in pure, but also quite a lot when you do the mechanics portion of the course. Keep working hard. Please remember to subscribe, that'd be very nice of you, and I'll see you all soon. Thanks again.